Article on Big Think on April 18, 2023 titled All of Our Theory of Everything are Probably Worn. The idea behind the theory of everything is to provide a single, unified framework that explains all physical phenomena in the universe. While many physicists believe that such a theory is possible in principle, there are challenges that make it difficult to achieve in practice. For example, one of the main challenges is reconciling quantum mechanics and general relativity, which describe the behavior of particles on small scales and the behavior of gravity on large scales, respectively. These two theories appear to be incompatible with each other, which has led to the development of various proposed theories of everything, such as string theory, loop quantum gravity, and emergent gravity, among others. String theory. String theory is a theoretical framework in physics that attempts to explain the fundamental nature of the universe. It proposes that the most basic building blocks of the universe are not particles, as in traditional particle physics, but rather tiny, one-dimensional objects called strings. These strings vibrate at different frequencies, and the way they vibrate determines their properties, such as their mass and charge. String theory proposes that there are many more dimensions to the universe than the 4 dimensions of spacetime that we experience in our everyday lives. It suggests that there could be as many as 10 or 11 dimensions, with some of these dimensions curled up or compactified in a way that makes them too small to be detected. One of the key motivations for string theory is to provide a theoretical framework that unifies all of the fundamental forces in the universe, including gravity, electromagnetism, and the strong and weak nuclear forces. This would result in a so-called theory of everything that could explain all physical phenomena in the universe. However, string theory is a highly mathematical and abstract theory, and it has yet to be confirmed by experimental evidence. Additionally, there are many different versions of string theory, each with its own set of assumptions and predictions. As a result, it remains a topic of ongoing research and debate in the field of theoretical physics. Loop quantum gravity. Loop quantum gravity is a theoretical framework in physics that attempts to describe the fundamental nature of space and time in the universe. In loop quantum gravity, space and time are quantized, meaning that they are thought to be composed of discrete, indivisible units. These units are called loops, and are thought to be the smallest possible units of space and time. The theory proposes that the loops can combine to form a 3-dimensional network called a spin network, which describes the geometry of space at a particular moment in time. One of the key features of loop quantum gravity is the idea of quantum geometry, which describes the geometry of space at very small scales, where quantum effects become important. According to this idea, space is not continuous and smooth, as in classical physics, but rather is composed of discrete, quantized units. Loop quantum gravity has yet to be confirmed by experimental evidence, and it remains a topic of ongoing research and debate in the field of theoretical physics. Entropy emergent gravity. Emergent gravity is a theoretical framework that proposes that gravity, the force that governs the behavior of objects with mass in the universe, is not a fundamental force of nature, but rather emerges from the collective behavior of particles in a system. According to this theory, gravity is not a force that particles feel because of their masses, but rather arises from the interactions of many particles in a system, in a way that is similar to how temperature and pressure emerge from the collective behavior of particles in a gas. One of the key motivations for emergent gravity is to address some of the problems that arise when trying to reconcile general relativity, which describes gravity on a large scale, with quantum mechanics, which describes the behavior of particles on a small scale. Emergent gravity is still a topic of ongoing research and debate, and it remains to be seen whether it can fully account for the behavior of gravity in the universe. Quantum field theory, QFT, is a framework in theoretical physics that describes the behavior of particles and their interactions in terms of fields. It is one of the most successful and well-established theories in modern physics, and it has been extensively tested and confirmed by experimental evidence. The Standard Model of Particle Physics is a theoretical framework that describes the fundamental particles and their interactions. It is a widely accepted theory that explains the behavior of subatomic particles, including the electromagnetic, weak, and strong nuclear forces. The Standard Model is a specific example of a quantum field theory. Quantum field theory is a theoretical framework that combines quantum mechanics with special relativity to describe the behavior of particles and their interactions. It describes particles not as discrete objects, but as excitations of underlying fields that permeate all of space and time. The theory of everything, TOE, is a hypothetical framework that aims to explain all the fundamental forces and particles in the universe in a single, unified theory. It would provide a complete description of the behavior of matter and energy at all scales, from the smallest subatomic particles to the largest structures in the universe. QFT is one of the main tools used by physicists in their attempts to develop a TOE. It is believed that the unification of all the fundamental forces, including gravity, into a single theory would require a quantum description of gravity, which is currently lacking. Several attempts to develop a TOE, such as string theory and loop quantum gravity, rely heavily on QFT and incorporate it into their frameworks. However, QFT alone does not provide a complete TOE, as it does not incorporate gravity into its description of particle interactions. However, these proposed theories have yet to be confirmed by experimental evidence, and some physicists remain skeptical of their validity. Additionally, even if a theory of everything is developed, it may not necessarily be complete or fully accurate, as new discoveries and phenomena could require modifications to the theory in the future. Ultimately, the article suggests that the quest for a theory of everything remains an important and ongoing endeavor in modern physics. Thanks.